this video, I'm going to demonstrate how to graph a particular polar graph in the Connect and ALEKS systems. So our directions are to graph the polar equation and then plot exact points using the plot a point tool. So the equation is r is equal to 3 times the cosine of 5 theta. And I want you to pay attention to that second that second sentence in the problem description. Already it's telling us that we're probably going to need to plot some points using the plot a point tool, which means more than likely all the points we want to plot are not going to fall on the grid as it is currently labeled. So we're going to anticipate that from the beginning. Okay. Now, as with any graph, we want to make sure we do as much as we can on paper, not only to get the practice and make sure we're confident in graphing by hand, but also so that we have something to fall back on to make sure we're generating graphs accurately. If we make a mistake, it's best to have something on paper because it's going to be easier to check our work from the paper. So this particular equation, r is equal to 3 times the cosine of 5 theta, falls under a class of equations that result in graphs called roses. So this particular graph, when we graph this graph from this particular equation, it's going to have kind of a flower shape. So fortunately, we already have the correct shape tool built into our Connect Math and ALEKS toolpad. We'll just use the tool in order to graph this particular shape. But of course, we need actual points to plot. So let's start on paper and then we'll transition to the homework system and we'll make sure we can graph it in the system as well. So let me switch screens, give me just a moment, and pull up the calculator. Okay, so here's our equation. R is equal to 3 times the cosine of 5 theta. So we can actually make some pretty helpful generalizations about what this graph is going to look like just based on the form for this equation. So first off, again, this is going to be a rose-shaped graph. It doesn't really look like a traditional rose. It looks more like a daisy if you were to compare it to anything, but we call this particular graph shape a rose. Now the 3 and the 5 also give us very important information about how this graph is going to look. So the 3 is actually going to tell us the length of each of the petals. So each of the petals is going to be length 3. So we have length 3 petals. So that means if we graph and we look for the tip of each petal, the tip of each petal is going to be on the third ring out from the pole, from the center of the polar coordinate plane. Now the 5 is going to tell us how many petals we should expect. Now there's two different situations. If this number in front of theta is even, then the number of petals is going to be double that number. So for example, if this was 2, we'll double that and we'll have 4 petals. It'll look like a 4-leaf clover. If we have the number 4 here, we'll double that and we'll have 8 petals. If the number instead is odd, like this 5 that we have here, that's going to be the number of petals. So we will have 5 petals in total. Now in the situations where we have an odd number of petals, that's typically where we run into problems with generating the points we need just from the grid as given. So the fact that we have an odd number of petals means not every petal tip is going to fall along a radian measure that we already have labeled on our grid. That's where we'll go to using the point plotter if we end up needing it. Okay, so as with many more complicated polar equations, it's best to start with the symmetry test because if we can use symmetry, if we can confirm that this equation is going to have particular types of symmetry when we graph it, we can save a little bit of time when it comes to plotting points. So we have our 3 types of symmetry: polar axis, which is your horizontal axis, theta equals pi over 2, which is your vertical axis, and the pole, which is the origin in the polar plane. So we're going to make each of these corresponding replacements, simplify the equation, and see if we can get it to match the original. So in order to test for polar axis symmetry, I'm going to replace theta with negative theta in my equation. So r is equal to 3 times the cosine of 5 times negative theta. Okay, then I go to my even, odd, or my parity rules. Cosine is going to be an even function, which means the cosine of negative theta is the same thing as the cosine of positive theta. So that means this negative here essentially is going to disappear because cosine is an even function. So this is going to be the same thing as r is equal to 3 times the cosine of just plain old 5 theta. Okay, so in simplifying this equation, we're able to get it to match the original. If it matches the original, then that confirms that we have that particular type of symmetry. So as we plot points, we can use the fact that our graph is going to be symmetric across the polar axis to save us a little bit of time and help us plot more points. Okay, now let's test the vertical axis theta equals pi over 2. We're going to replace theta with pi minus theta and then simplify the equation and see what results. So r is equal to 3 times the cosine of 5 times pi minus theta. So this is going to take a little bit more work with our simplification. So let's start by distributing that 5. So 3 times the cosine of 5 pi minus 5 theta. Okay, and now we have a cosine difference. So in order to simplify this correctly, we'll use the cosine difference formula. So what that formula states is that if we want to take the cosine of a difference, that's going to be the same thing as the cosine of the first angle times the cosine of the second angle. And then we're going to switch the sign. So difference here becomes sum when we execute the formula. And then we're going to take the sine of the first angle, multiply by the sine of the second angle, and that's going to be everything. That's our formula executed. Okay, so cosine of 5 pi is a constant. That's a particular constant radian measure. So this we can simplify. Same thing for sine of 5 pi. Now you may be thinking 5 pi, that's not something I see on the unit circle. Remember, in that case, we use coterminal angles. So 5 pi, since it's an odd multiple of pi, it's going to be coterminal with pi. So in place of 5 pi, we can think of it as just pi, and then we can find the trig values accordingly. So the cosine at 5 pi, or the cosine at pi, is going to be -1. So that'll be a -1 right there. The sine at 5 pi, or the sine at pi, is going to be 0. So this will be 0, which means this term is going to disappear. So we're going to be left with our 3, a -1, and then the cosine of 5 theta. So if we simplify all of that, that's going to be r is equal to 3 times -1 is -3 times the cosine of 5 theta. And so notice this equation is very similar to the original, but it doesn't quite match because of that negative. So that means that this particular symmetry test is inconclusive. It doesn't necessarily mean that our graph won't be symmetric across this particular line. It just means we can't confirm it algebraically. And then our final test, this final type of symmetry is pretty rare, but we're going to test it anyway. So pole symmetry is like origin symmetry. Think of it as a 180-degree rotational symmetry, or a double flip, a double fold. If it's symmetric across itself when we fold it horizontally and vertically, then we say that the graph has symmetry with respect to the pole. So we're going to replace r with -r, and then just see what happens. Okay, now as usual, the goal is to see if we can get this equation to match the original. This negative is going to be impossible to get rid of without changing the sign on the other side. So what that essentially means is we're stuck. We can't simplify this equation to the extent that it's going to match the original, so we know this test is inconclusive as well. Now again, we may find that when we graph, we do have symmetry with respect to the pole. It just means we can't confirm it using algebra. Okay, so we did have one successful symmetry test, and we'll use that to our advantage in order to save ourselves a little bit of time. Now let's go through and let's identify some points, and then we'll plot them as we go. So we're going to plug in our standard radian measures for theta, and then find the resulting value for r. So we'll start at theta equals 0, which means we're starting along the polar axis. So remember, our equation is r is equal to 3 times the cosine of 5 theta. So we're going to plug in our values of theta to that equation. So plugging in 0, okay, so that's going to be 3 times the cosine of 0, 3 times the cosine of 0. Okay, and at 0 radians, we know the cosine has a value of 1. So that's going to be 3 times 1, which is 3. Okay, so let's put that on our graph. So at 0 radians, our value of R is 3. So at 0 radians, we're at 1, 2, 3. Okay, now in terms of symmetry here, remember we have symmetry with respect to the polar axis, which is our horizontal axis. This point that we plotted is already on that axis, so we don't have a point that's specifically symmetric to this one. If we have something above that point or below that point, then we can use symmetry. But here, this point is going to be unique and it's not going to have another symmetric point. Now, for pi over 6, we will be able to use the symmetry. So let's plug that in. So R is equal to 3 times the cosine of 5 times pi over 6. Okay, so cosine of 5 pi over 6. Okay, so at 5 pi over 6 radians, our cosine is going to be negative root 3 over 2. So we'll have 3 times negative root 3 over 2. So that's going to be negative 3 root 3 over 2. Now, when we plot in the homework system, if we wanted to plot this particular point, this would be the value that we would use, and we would have to use the point plotter, type in this value along with our radian measure pi over 6. Okay, now when we put this on paper though, we need something that's going to be a little bit more visually meaningful. So that's when we'll put this into the calculator and we'll get an approximation. Now you can do this a couple different ways. You can approximate this value, or you can just type in the actual expression here and see what the approximation is from the very beginning. Now, notice what we're plugging in is in radians, so we could change our calculator to radian mode and evaluate with an input of pi over 6. However, another option that may be a little bit easier to type and may save you a little bit of time is to actually just leave your calculator in degree mode and then type in the corresponding degree measures based on whatever the radian measure is inside of your trig function, because typically those numbers are a little bit faster and a little bit easier to type. So it's really just personal preference, but keep it in mind you do have some options here. Okay, so we have 3 times the cosine of 5 pi over 6 radians, which is the same thing as 150 degrees. So there we go, that's going to be our approximation. Notice it's negative. Our exact answer was negative. Our approximation is negative as well. So it's approximately negative 2.6. Okay, so let's put that onto our graph now. So at pi over 6 radians, which is going to be right here, we are at about negative 2.6. So negative 1, negative 2, negative 2.6. So notice when we're graphing something that's negative, we're starting along that particular axis and then we go in the opposite direction. That's what a negative value of R means. Now we have the opportunity to use our symmetry test. So we're symmetric with respect to the polar axis, our horizontal axis. This point was plotted below, so that means we have to have a symmetric point that would be plotted in essentially the same location above the polar axis. So there's our free point. Okay, and what I'm going to do, because the roses are a little bit more difficult to follow in terms of what point is followed by which point and so on and so forth, I want to number these points as I go, because this is going to tell me what order to connect them in order to get an accurate shape. So this was the first point we plotted, this was the second point we plotted. So as we connect them, we'll connect them in the order based on how they were plotted. Okay, that's not enough to get a sense of shape, so let's go and let's plot some more points. So pi over 4, so we have R is equal to 3 times the cosine of 5 times pi over 4, or 5 pi over 4. Okay, so at 5 pi over 4 radians, our cosine is going to be negative root 2 over 2. So 3 times negative root 2 over 2, or negative 3 root 2 over 2. So there's our exact value. And we'll approximate that so we can graph it a little bit better on paper. So 3 times the cosine of 5 pi over 4, otherwise known as 225 degrees. And we get about negative 2.1. Okay, so let's put that onto our grid. So at pi over 4 radians, we're at negative 1, negative 2, just a little bit past negative 2, which would be right here. So that will be our third point. And again, we can use symmetry to graph a corresponding point that would be above the polar axis, and that point would be about right here. Okay, let's keep going. Pi over 3, so r is equal to 3 times the cosine of 5 times pi over 3. So 5 pi over 3. We know the cosine at 5 pi over 3 radians is going to be 1/2. So that's going to be 3 times 1/2. Now notice the value went positive here. So we've gone from positive to negative to negative to positive. Things get a little crazy when we're plotting points with arrows. That's one of the reasons why it's helpful to number those points so we know what order and to connect them in order to get the most accurate graph. Now 3/2 is the same thing as 1.5. So we can use 1.5 as a way to visualize where our point's going to be. So at pi over 3 radians, which is right here, we're going to be at r equals 1.5, right here. So that's going to be our fourth point. Okay, and then we're almost to the first quadrant. It's really weird because notice all these points we've graphed didn't truly graph all in the first quadrant. That's the nature of graphing something like arrows. Okay, and then if we want to use our symmetry as well, we can do that. So there's a point above. Let's graph the corresponding point that would be below the polar axis. Okay, so it's hard to get a sense of the shape right now. Just go with it. We'll plot all our points, and then we'll go from there. And we can use what we know about the shape of arrows to help us graph a little bit more easily. So ending the first quadrant, we're now at pi over 2 radians. So r is equal to 3 times the cosine of 5 times pi over 2. Now 5 pi over 2, we don't see that value labeled on the unit circle, so we use coterminal angles. 5 pi over 2 is going to be coterminal to pi over 2. And at pi over 2 radians, we know that the cosine is 0. So that's going to be 3 times 0, which is 0. So at pi over 2 radians, our r value is 0, which means we have a point here at the pole. So that is going to be our fifth point. Okay, let's keep going. Again, it looks kind of messy. I promise everything is going to make its way together and it's going to be a nice pretty graph. And we'll see all the symmetry and execution when we actually connect our dots. So 2 pi over 3, that's going to be our next radian measure. Now we're transitioning from quadrant 1 into quadrant 2. So r is equal to 3 times the cosine of 5 times 2 pi over 3. Okay, so that's going to be 10 pi over 3. Now 10 pi over 3, we need to find something that's coterminal to that. 10 pi over 3 is going to be coterminal to 4 pi over 3. So 10 pi over 3, if we want to write it down just so we have a note, 10 pi over 3 is going to be the same thing as 4 pi over 3 in terms of what it's coterminal to that we see on our unit circle. So at 4 pi over 3 radians, our cosine is going to be negative 1/2. So we have 3 times negative 1/2, or negative 3/2, which is the same thing as negative 1.5. So when we get to 2 pi over 3 radians, which would be right here, we are at negative 1.5. So 2 pi over 3, negative 1, negative 1.5. Okay, it looks like we've already got that point. Hey, we got that one from the symmetry, right? That's one of the things that the symmetry does for us. It saves us some time. Okay, now keep going. 3 pi over 4. R is equal to 3 times the cosine of 5 times 3 pi over 4. So that's going to be 15 pi over 4. Now 15 pi over 4 is going to be coterminal to 7 pi over 4. So that's the same thing as 3 times the cosine of 7 pi over 4. Okay, so 3 times the cosine of 7 pi over 4. Well, the cosine of 7 pi over 4 is going to be root 2 over 2. So root 2 over 2. So we'll have 3 root 2 over 2. And if we want an approximation of that, let's see if we can type this one in without using the trig function. Let's just type it in as 3 root 2 divided by 2. Here we go, about 2.1. Okay, so at 3 pi over 4 radians, we're at about 2.1. Okay, well, we have that point as well. So if we keep tracking the numeric order of these points, 1, 2, 3, 4, 5, this was the 6th point, this is the 7th point, and you can probably guess that this next point is going to be the 8th point. We can confirm that here by evaluating at 5 pi over 6. So r is equal to 3 times the cosine of 5 times 5 pi over 6. Okay, so that's going to be 3 times the cosine of 25 pi over 6. Now 25 pi over 6, let's go out to the side and let's figure out the coterminal angle for that. So 25 pi over 6, if we subtract 2 pi, that's the same thing as subtracting 12 pi over 6. Okay, so that's going to give us 13 pi over 6. Now that's still not where we normally like to see things. That's still not within our first rotation around the unit circle. So we can subtract another rotation, and then we can get back to pi over 6. So 25 pi over 6 is coterminal to pi over 6. We can replace it with pi over 6. So 3 times the cosine of pi over 6. And at pi over 6 radians, the cosine is root 3 over 2. So 3 times root 3 over 2, or 3 root 3 over 2. Again, if we want an approximation of that, 3 times the square root of 3 divided by 2. So about 2.6. Notice if you look at some of these values, we can see a lot of symmetry here. Here at 0, 1.5 and negative 1.5, negative 2.1, positive 2.1, negative 2.6, positive 2.6, which means you can probably guess what's going to happen here at pi. Okay, so at 5 pi over 6, here's 5 pi over 6, we're at 1, 2, about 2.6. So that confirms that that's the point that we want. Okay, now at pi, we've gone first quadrant, now we're concluding the second quadrant. So r is equal to 3 times the cosine of 5 times pi. 5 pi, because it's an odd multiple of pi, is going to be coterminal to just pi. So cosine of 5 pi is the same thing as cosine of pi. So 3 times the cosine of pi. And we know that the cosine at pi radians is going to be negative 1. So that's going to be 3 times negative 1, which is negative 3. Again, notice those symmetric values, not a coincidence. Okay, so at pi, we are at negative 3. So that's negative 1, negative 2, negative 3 right here. So our 9th point and our first point coincide with one another. So what's happening here? We have all these points that are traveling in a very specific order, and if we were to trace them, I'm going to show you how to do this. You don't actually transition through the quadrants the way you would think you would. You kind of swoop and create half petals before you conclude a petal. So what you're going to find is that there's going to be a petal right here. Okay, that's going to be one of your petals. And the way we actually transition across that petal, we don't complete a petal all at once. We start here and we actually end up going through the pole using a radian measure that we didn't calculate with. But we transition through the pole and then we come around like this. Okay, that was 3. Here's 4. 4 go through and hit 5. 5 go through and hit 6. 6 go through and hit 7 and 8, and then we would come full circle and we would complete the rows. Now this is a very inaccurate graph of a rose, and one of the reasons it's inaccurate is because we're supposed to hit the third ring each time we hit the tip of a petal. So this right here should actually be along the third ring. Same thing right here, same thing right here, Same thing right here. But you'll find that it's difficult to get these kind of graphs exact when we're graphing roses. And one of the main reasons it's difficult to get those tips of petals exact is because they're not going to fall along those standard radian measures we graphed, with the exception of the point at 0 radians and the point at pi radians. Everything else is really just approximated. But we know each petal is supposed to have a length of 3, so each time we graph a petal, it needs to fall along the third ring. But we don't actually see that happening with the numbers we're plotting. Now, we could certainly keep going and we could look at some additional radian measures, but you're going to find that the same is going to result. You're going to end up with fractional values that you approximate, and you're not going to find the tips of the petals. Now, that is potentially a problem, because what you're going to find is when you put this into Connect Math, what it's going to ask you is, number one, what kind of graph is this? So ALEKS Connect Math, we know it is a rose, so you choose the rose tool. Then it's going to ask you how many petals you want. Okay, well, we know there's 5 petals. What it's then going to ask you to plot is where the tips of the petals are. And based on the points that we were able to plot accurately, we only know where one petal tip is. So that's going to be one of the petal tips. But the other 4, we only really have a sense of where they would fall, and they don't appear to fall on the actual grid as we have it labeled. Remember though, that second sentence in the problem description said use the point plotter tool. Okay, so they were already kind of giving us an indication that maybe we need to do something like that, that just graphing by hand and using standard radian measures may not be quite enough. So I'm going to show you a technique you can use to determine where those petal tips are going to fall so you can get those graphed accurately. So what you're going to have to do is you're going to have to kind of rethink the problem a little bit. We're graphing it in polar form, but I want you to pretend for a minute that this was not a polar graph. What if instead you were graphing y is equal to 3 times the cosine of 5x? What if you were graphing this in terms of x and y instead of in terms of r and theta? If you think about it that way, that's going to give you a way to find these petal tips more accurately. Okay, so if we were going to go about graphing this particular function, what would we need to do? Let's review that a little bit. So first thing we would look for is the function's amplitude. Okay, so we would have an amplitude of 3. What does that mean? That means when we go to our high point and our low point, our relative maximum and minimum values, they're at 3 and -3. Now they could shift, of course, but because we're not adding on a number here, we haven't shifted. So our center is at 0, our max is at 3, our minimum is at -3. And then we would label across our horizontal axis based on the period for our function. So our standard cosine period is going to be 2 pi, and we know we always divide it by whatever the coefficient on x is. So 2 pi divided by 5, that's going to be our period. Okay, now the other thing we did when we graphed this particular kind of function is we set up an inequality to determine where each period is going to start and where it's going to end. So the standard period is going to start at 0 and end at 2 pi. In this case, the period will start at 0 and end at 2 pi over 5. So if we were to start labeling based on that, remember we divide our graph into 1, 2, 3, 4 equally sized intervals. And again, we're starting at 0. We haven't shifted left or right, so we're starting at 0, and then rather than ending at 2 pi, we're ending at 2 pi over 5. Okay, then we need to label in the middle, and this is where it's crucial. This is the moment when we're going to be able to identify what's going to be reflected on our polar graph using this different perspective on this particular function. So remember, we're taking the whole period, dividing into 4 parts. So 2 pi divided by 5, our period, divided into 4 equally sized intervals. So that's going to be 2 pi divided by 5 times 1/4. Okay, our 2 and our 4 can reduce, leaving us with a 2 in the denominator. So that is going to be pi over 10. So pi over 10 represents the width of each of these equally sized intervals. It tells us how to count as we move across this horizontal axis. So starting at 0, counting by pi over 10. Add on pi over 10. Here's pi over 10. Add on another pi over 10, we get to 2 pi over 10, which reduces to pi over 5. Add on another pi over 10, 2 pi over 10 plus pi over 10 is going to be 3 pi over 10, which does not reduce. And then 3 pi over 10 plus pi over 10 takes us to 4 pi over 10, which reduces to 2 pi over 5. That's exactly what we expect. That's exactly what we want. And then if we were to fill in the points from here, remember cosine is going to start at its relative maximum, so they're at 3. And then we go down to our midline, we hit our minimum, we go back to our midline, and then we hit the maximum again. Okay, and then we would connect the shape, again graphing in terms of x and y, not in terms of r and theta, and that would be the shape. So how does this fit into what we're doing with polar graphing? Well, the petal tips, this was one of them. Notice what the ordered pair would be for that. When theta was 0, r was 3. So the point would be 3, 0. Notice this point we have right here would be the point 0, 3. It's not a coincidence that these two appear to be basically the same thing except flipped. When we think of 0 as the input, 3 is what we get as the output. Okay, so this maximum value corresponded with one of the petal tips, and that is actually going to be a consistent pattern anytime we hit a max or a min on our cosine functions graph. So this particular point also corresponds to a petal tip because it represents an extreme value for our function. This one does as well. So this particular point at pi over 5, negative 3, if we put it in polar coordinates, pi over 5, negative 3 would become negative 3 pi over 5. That will be the location of another one of our petal tips. Let's see how that looks on our graph. So at pi over 5, which would be between pi over 6 and pi over 4, we have a petal tip at negative 3. That's this tip over here that we weren't really able to accurately graph. So we've got this one accurately. The next one, this one over here, these are the coordinates for it. Same kind of thing here. When we graph using x and y, we have an input of 2 pi over 5, we have an output of 3. When we put this in polar coordinates, that's going to be 3 and 2 pi over 5. Okay, and that's going to be another one of the tips. Now, we're supposed to have 5 petals. That only covers 3 of our petals, so how do we get the rest of them? Remember, this is really just a snapshot of this whole functions graph. If we were to essentially copy and paste this and keep going, we can get additional points, and that's where those additional petal tips are going to come from. So imagine just continuing to count by pi over 10, and we can find the additional petal tips. So starting at 2 pi over 5, now that's the same thing as 4 pi over 10. Next thing we would go to is 5 pi over 10, which would be pi over 2. 6 pi over 10, which would reduce to 3 pi over 5. 7 pi over 10. Okay, if we need to keep going, we'll keep going just in case. 8 pi over 10, which reduces to 4 pi over 5. And you can probably start to see the pattern. 8 pi over 10, 9 pi over 10, and I'm about to fall off the page, so let's see if that's going to be enough. So starting back at the max, we go to the midline, we go to the minimum. Okay, there's another petal tip. Go back to our midline, and then we hit our maximum again. Okay, so if we graph that additional period, we have an additional petal tip and an additional petal tip. Okay, so the ordered pair here, we'll go ahead and write them in the correct polar form. We're at negative 3, 3 pi over 5, and right here we're at positive 3, 4 pi over 5. Those are going to be the accurate tips for this particular sequence of petals. And notice again, pi over 5, 2 pi over 5, 3 pi over 5, 4 pi over 5. Those are not things that fall on our standard polar grid, which is why we weren't able to get them just by plotting points like we normally do. Okay, so when we transition back over to the homework system, we're going to use these points we've identified, use that point plotter tool, type in the coordinates, and then the tool for the rows graphing will snap to these locations that we need. So let's flip back over to the homework system and let's see if we can get that graphed accurately. Give me just a minute. Okay, there we go. So flip back over, here we go. Okay, so we're going to use our point plotter, go ahead and graph everything we need, because notice we're counting by pi over 6, pi over 4, and that's not going to be enough for us. So plotting a point, our first point was at 3, 0. Okay, so I'm going to type in the coordinates 3 and 0, and then we'll plot that point. Okay, notice it plots it for me, so plot it. The next petal tip we found was at -3 pi over 5. So -3, and then we'll use the fraction tool, use our pi, and then pi over 5, and it's going to plot it. That's going to be another one of the petal tips. Okay, next petal tip is at +3, 2 pi over 5. So +3, use the fraction, 2 pi over 5, plot it. That's going to be another one. Okay, our next one, -3, 3 pi over 5. So -3, and then use the fraction, 3 pi over 5. Plot that one. And then our last petal tip we identified was at +3, 4 pi over 5. So +3, here's our fraction. Oops, let's fix that. +3, and go over to the next box. There we go. And then 4 pi over 5. Plot that point. Notice if you look at the points where they are, they're symmetric. They're evenly spaced around the coordinate plane. That's not a coincidence. That's what we expect. So if we were to connect them, we could almost form a star. In this case, our star is going to look like a flower. So now we can go to our rose shape. Okay, notice it's going to offer us all the different options. We know we have 5 petals, so I'll select that. And then we have to place our petals based on where the tip falls. So here's the first petal. Each of our additional petals is going to fall with a tip at each of these locations we plotted using the point plotter. So we're going to place all of them carefully, and then it's going to connect it, and we have our rose. And it looks similar. It's a better version of what we did by hand, but it's an accurate version of what we did by hand. So let's check it. And perfect, there's our rose. So graphing something like a rose is probably one of the more challenging things we do in polar coordinates. It's kind of a satisfying graph to generate, but it's definitely not an easy graph to generate. So understanding something about the symmetry of the graph, and then falling back on what we know about the equation and what the equation tells us about the shape, we can determine it's a rose based on having a multiple of theta within our sine or cosine. That multiple is going to give us information about how many petals the rose is going to have, and then whatever the coefficient for the function is, that's going to tell us what the length of each petal is. So knowing some of those things helps us, but again, there's that trick for graphing in Connect Math or ALEKS. If we can graph in terms of X and Y initially, identify those relative max and min points, that's going to tell us where the tips of the petals fall, and it's going to allow us to generate a more accurate graph. So that is graphing a rose in the ALEKS and Connect system.